Hello, and welcome to another lecture in the course. So we're looking at the mean value property for harmonic functions, and this is subsection 7.2.2 in the book. You can get the book in the link in the description, either as a PDF or you can buy a paperback if you want. All right, so let's motivate this a bit. So let's suppose that we instead of in the plane, let's suppose that we look in R, right, on the real line. And so what would harmonic mean? It's the same thing. It should be a function whose Laplacian is 0. But if we have just one variable, if we look at the Laplacian, right, there's only, well, looking at the derivative in x, the second derivative in x, there's only one variable now, x, f, so it's just f is just a function of one variable, real valued function of one real variable. Second derivative is 0. Well, that just means the function is some ax plus b for two constants, a and b. It's affine linear, right? So those are all the harmonic functions. Now, if we if we look at affine linear functions, then one of the things that they satisfy is this sort of property for any interval ab, right? If I look at the value of the function in the middle of the interval, it's the average of the values at the endpoints, right? And you just get that by plugging in this thing, right? It's immediate. Now, what you can actually prove is that this actually characterizes the affine linear functions or harmonic functions. So it's an exercise that if you start with a continuous function f, it is harmonic, meaning affine linear, if and only if this thing holds for all intervals. So you can make it into the property that defines what harmonic functions are. So we want the same thing for harmonic functions in a plane. So let's look in the plane. So here is the plane version of this. So of course, in the plane, there's a lot more harmonic functions than just affine linear, and we really have to replace the interval with the analog in the plane, which is a disk, right? So suppose that we have an open set, then a continuous function f on that open set is harmonic, if and only if for every point there is some maximal radius. Let's not worry about it at the beginning too much. There's a maximum radius such that the disk of that radius still fits in U, and you have for all the radius smaller than this radius, you have the mean value property, right? So you have that the value of the function is equal to its average on the circle of radius little r, right? And so, and this R, this capital R, it doesn't have to be the maximal one that fits in U. It just means that there is some capital R at every point, right? So it really says that we have that it's harmonic. The f is harmonic if and only if you satisfy the mean value property on all small enough circles, right? That's what it says. And moreover, if it is actually harmonic, then we've actually seen, this is what just from solving the Dirichlet problem. So we talked about it last time. We actually saw that a harmonic function actually satisfies this mean value property always. So once it's harmonic, you could actually pick this capital R to be as big as possible, which would be the biggest one that's still where the disk still fits in U, right? So, but basically, the main thing is that if you satisfy the mean value property for all disks or all small enough disks, then you are harmonic is the main thing here, right? Because the other one we've essentially proved the other direction. All right, so well, let's look at the other direction. So let's start with what we've basically proved. So suppose that you have a harmonic function and you have a disk, a closed disk that's completely in U. So basically, what it means is that we're picking this capital R as large as we want, right? So let's solve the Dirichlet problem in this disk, right? So that means I just apply the Poisson formula, right? And if we apply the Poisson formula and plug in the center point we saw last time, well, that's what we're doing here. We're then the Poisson kernel just kind of disappears, becomes constant, right? So we just have the 1/2 pi, right? And I've pulled that out. So that means we get the average value of f on the circle is, well, we plug it into the solution of the Dirichlet problem, and that's just f because we're starting with a harmonic function, and harmonic functions are, the solution of the Dirichlet problem is unique, right? So once, if we're looking at the value of the function on the circle, right, that gives you a unique function inside the disk. So we already have one that's f. So the solution of the Dirichlet problem has to be equal to the value of the function, and we're just plugging in the center point here, right? Well, but that just means that we have the mean value property here, right? So this direction is easy. So let's do the other direction. Let's do the hard direction, the direction that we haven't talked about yet. So suppose that f is continuous and satisfies this mean value property from the theorem, right? So now suppose that we have some closed disk in U that's completely in U. So centered at Q of radius S. Let's solve the Dirichlet problem with f, with the values of the function f on the boundary of this disk, and let's solve inside. Now we don't know that f is harmonic, right? So we'll get some other function, well, possibly other function, h, that's defined on the closed disk, and it's harmonic inside, right? And it equals f on the boundary. That's what we're getting, right? Now, let's look at their difference. So let's look at f minus h, right? So on the boundary of this little disk, this guy, well, they're equal, right? So this phi is going to be 0, right? It's identically 0 on the boundary. It's continuous because both f and h are continuous on the closed disk. So this phi is a continuous function on the closed disk. It's identically 0 on the boundary, as I said, and it satisfies the mean value property on the same circles that f does, right? I mean, for each point, f satisfies for all small enough circles. H, of course, satisfies the mean value property on all circles that will fit in U, right? Whenever I have a disk that's in U, then H satisfies the mean value property on those circles. F maybe satisfies it on just all the small enough ones. So whenever F satisfies the mean value property, H does as well, and therefore phi does, right? So we have a phi that also satisfies the mean value property, and it's 0 on the boundary, and that's the key point. So suppose for contradiction that this phi attains a maximum somewhere inside, and that maximum is bigger than 0. It's actually positive, right? And it's somewhere inside. Now, because phi is 0 on the boundary, this set of points where phi is maximal, this x, is compact because it's definitely a closed set of this disk, but it also doesn't doesn't have any points on the boundary because on the boundary phi is 0, right? So it's not equal to phi of p, which is positive. So this is a compact subset. It's actually a compact subset of the inside of the disk, right? All right. Now, suppose that p, not just that it's one of these random points of the maximum, right? Maybe it attains the maximum only at one point, maybe at many points, but suppose it's the one that's closest to the boundary of this disk, right? It's a compact subset inside, right? Doesn't contain any point of the boundary, so therefore, it's some positive distance away from the boundary, and so we can pick one that's closest to the boundary, and suppose we take this little circle around P. So we put a little disk around P over here, right? This guy that's still inside, actually well inside this disk. It's inside the interior of this disk, and it's the R is also less than this R of P, of this capital R of P. So we know that this is going to be one of those disks that where F satisfies the mean value property, right? So it satisfies on this circle. Maybe it's a very small circle, right? Okay, so now if you look at this picture, well, it's kind of a proof by picture, but you can make this precise. Because this P was closest to the boundary, right? Then really this phi is for some open set of the open part of this arc. It has to be somewhere where phi is actually strictly less than phi of p. That means that it doesn't complete a line in X, right? In this set over here, because this was the point that was the closest to the boundary, right? So if I draw a little circle, somewhere on the circle I have to be even closer to the boundary, and then in a little neighborhood of those points, I can actually find some, let's call it capital C, some constant less than phi of p, such that phi is always less than that, right? So for some open subset, mainly that open subset has positive measure, right? So some open subset of the boundary. So just a little piece of arc, right? That's what I mean here. Not open subset in the plane, but open subset of this circle, right? So actually a little arc on some little arc of this disk, right? We have this inequality where C is strictly bigger than phi of p, right? But that means that if I take the average of phi on this circle, because phi of p is the maximum of phi, it's as big as phi gets on this entire disk, right, where phi is defined. It can't be anywhere where I'm integrating. It can't be any bigger than that, right? But on an open, on a little arc, it's actually strictly less than that. It's actually equal to some constant. You can easily see that this average has to be less than this maximum, right? So there's a strict inequality here, right? So we have that the average of phi has to be strictly less than the phi of p at that point. But that's a contradiction, because we said that phi of p satisfies the mean value property on the same circles as f, and we've picked this r to be less than capital R of p, and so we should have been satisfying the mean value property. Basically, what's happening is that if this is a maximum, then somewhere on this circle we would have to be if we're less than phi of p, we would have to be bigger than phi of p to make this inequality, and we know that we are not, right? We're always less than or equal to phi of p because that's the maximum. All right, so what does that mean? That means that there was, well, maybe there is a maximum, but it's not positive, right? I mean, there is a maximum. We're looking at a compact set, right? But it's not positive, right? So phi, whatever it is, it's less than or equal to 0, right? I mean, the maximum is actually going to be 0 because it's attained at the boundary as well. Like, we know that it's 0 on the boundary. And we know that there's no positive maximum. All right. So that means that phi is less than or equal to 0. And you can do the same thing just with looking at minimum, right? So look at a minimum and suppose that it's negative. And you can show that, well, that's also gets you contradiction. So therefore, phi is always bigger than or equal to 0. That means that phi is equal to 0. That means that f is equal to h. And therefore, f is harmonic because h is harmonic, right? I mean, we're really showing just that f is harmonic in a little neighborhood, but that's enough. That's all we need. We don't need to we don't need to show everything all at once. I mean, harmonicity is a local property. So if we prove it locally, we're good, right? So f is harmonic inside this little disk. This little disk was arbitrary. Therefore, f is harmonic, right? Because harmonic is just a property of like, we're taking derivatives, right? That's only local. All right. So we have the mean value property. The theorem is proved. Let's look at the some applications of this. So the first application of the mean value property, or one of the more useful things about writing a condition as an integral instead of as in terms of derivatives, is that normally if I have some C2 twice continuously differentiable functions, and I have a uniform limit, I can't just say that the Laplacian applied to this sequence is equal to the limit, Laplacian of the limit. That's just not true. I would have to have basically I would have to have the derivatives, all the derivatives, including the second ones. I have to have that those also converge, right? In which case, I mean that's kind of obvious then, right? So it's you have to for C2 functions you actually have to if you want convergence. The right sort of convergence would be actually that you're getting convergence including the derivatives. But that's not what we need. I mean, that would be stronger than what we need. Than what we're usually asking in this in all of this stuff, which is usually just uniform convergence, right? Or the topology that we've been so used to in complex analysis. Right, which is the right convergence for continuous functions, but it turns out it's the right convergence here as well, because for harmonic functions this is true. So basically, if all of these things are 0, then this guy is also 0. Right, that's basically what it says. So suppose that I have a sequence of harmonic functions, Fn, and suppose it converges uniformly in compact subsets to some f. Then that f is harmonic, right? So the uniform limit of harmonic functions is in fact harmonic, even though maybe it wouldn't be what we a priori expect for C2 functions, right? So firstly, uniform, if we have uniform convergence on complex subsets, blah, 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 we get continuous, right? So we get that f is automatically continuous. So therefore, we can apply the mean value property, right? So suppose that we take a little circle, so a little disk that's all the way inside U, and now we have this sequence of functions, right? It converges uniformly on compact subsets. The circle is compact. So therefore, the sequence converges uniformly on this circle. that means it goes inside integrals, right? The limit goes inside integrals. So at f of p, the center of this of this disk, right? Well, we have uniform convergence, we have pointwise convergence, right? So at this point, and now we rewrite this fn of p. We rewrite it as using the mean value property, as the average over this little circle, and now this limit can go inside because it's uniform on that. And so if the limit goes inside, I just get f inside. Well, we're done, right? Because f of p is equal to this this integral, right? The equals to its average on this circle. So basically, what we've proved is that actually the capital R of P is as big as you want, right? As long as this the disk fits in U, that's all we need, right? So we've proved for all disks that fit in U, we have the mean value property, right? And therefore, F is a harmonic, right? So that's a very neat application of this, right? Something that wouldn't be immediately obvious if you were just looking at the PDE version of the definition, right? That it's the functions where the Laplacian is 0, right? That would be hard to prove. So a couple of exercises. So first, prove the maximum principle for harmonic functions, which we proved using the maximum modulus principle for holomorphic functions, but prove it using the mean value property. And the point is that you don't really want to, it's kind of not nice to rely on the maximum modulus property for holomorphic functions because harmonic functions they work in other contexts than just in the plane, and you get holomorphic functions only in the plane. So really the maximum property, maximum principle, is something that is true for harmonic functions in any dimension, right? It's something that's just about harmonic functions themselves. So it's useful to have a proof that's purely in terms of harmonic functions. And so you can do it, and basically it's the same idea as how we proved the maximum principle, maximum modulus principle for holomorphic functions. We actually did it using Cauchy's theorem, and basically using Cauchy's theorem, we got that we actually got the mean value property for holomorphic functions, and then we use that, right? It's actually simpler for harmonic functions. It's only you need to have, because they're real valued. So it's you don't have to do like a two-step thing as we did for the maximum modulus principle. All right, but that proof would actually generalize to all dimensions, because you are also going to have this this mean value property in all dimensions, not just in the plane. Then the next exercise. So sometimes the mean value property is not given in terms of circles. Sometimes it's given in terms of disks. So if I, instead of average on a circle, I could average on a whole closed disk. So this is slightly simplified version without that R of P. So let's just suppose it's for all these disks. I mean, you could again do it just for small enough disks, but suppose for simplicity of statement, we write that the function satisfies the mean value property for disks. So this is a two-dimensional integral, right? This is 1 over the area of the disk. We're integrating with respect to area. So if I average f over the closed disk, an entire closed disk, that's equal to f at the center point. And again, that gives me an if and only if, and the proof is very similar. And to go, if you want to start with the mean value property, if you start with harmonic, then you want to go here. Well, just integrate with respect to R as well, basically, right? And use use polar coordinates, right? And the other direction, it's very similar to what we did, right? So, right, and one other note about this in the book as it currently stands, it's only if. Really, you should just prove if and only if, because that's that actually makes the exercise somewhat easier to do, even though it's a little bit more. But you sort of understand the relationship if you do an if and only if. And I will change it in the next version of the book. It's going to be an if and only if. All right. So so that's it for the mean value property. And next time we're going to look at Harnack's inequality and Harnack's principle. So. All right, so I'll see you then.